Hello, welcome to the final video on the topic of algebraic methods. So we're going to wrap up what we've done in the first 4 sessions, and today we're going to have a look in particular at the idea of disproving by counterexample, which once you've seen a few of how to do them, you should find this a fairly straightforward idea. So disprove by counterexample is quite a nice thing. So before we get started on this, I want to just show you, as ever, some warm-up questions. So 4 to have a go at. These might take you slightly longer than usual today, but they are obviously worthwhile, as they always are. Question 2 in particular, we're going to use this idea later on in this session. So try these, only once you've done your best on them, play the video to see what the solutions are. Then once you play the video having done them, make any corrections where necessary. So let's have a look at how to tackle question 1. So question 1 could be quite difficult. It's all about how you define the numbers. So use an algebraic method to prove that the sum of 3 consecutive whole numbers is always divisible by 3. Now, we need to think of the number line slightly differently. Because we're wanting to find if it's divisible by 3, we're going to have to write the numbers as multiples of 3 if possible. So I'm going to start by saying, let k, could be any letter, I'm just going to go for k, let k be a natural number. Okay? Then what we can say is if we have a number which is 3 times k, then the next one along from that will be 3k plus 1. And the next one along from 3k plus 1 will be 3k plus 2. And so by writing the first number as 3k, you can see that the next number along will be 3k plus 1, and the next one after that would be 3k plus 2. Then I'm going to just put in brackets, the next one will be 3k plus 3, which equals 3 lots of k plus 1 if we factorised out of 3. And so this here would be a multiple of 3 as well, because it has a factor of 3 in it. And this one here, 3k, can be divided by 3. 3k divided by 3 gives you just k. So the idea is, by writing it like this, you can see that any row of 3 consecutive whole numbers will have to have a multiple of 3. So I'm going to get rid of this now because I've shown you. But by setting it out like this, we're almost done. So the product, we can just work out and show that it's going to be a multiple of 3. So first of all, 3k, 3k plus 1, 3k plus 2, they're going to be consecutive whole numbers. The product of them is going to be 3k multiplied by 3k plus 1 multiplied by 3k plus 2. So if I just write this explicitly as a multiple of 3, I can say this is 3 multiplied by k, 3k plus 1, 3k plus 2. So by writing it in this way, we can see clearly that this is a multiple of 3. Because we've just factorised out very clearly this 3 here. If something's a multiple of 3, that's the same as saying it's divisible by 3. So therefore, we just now conclude by making reference to the initial statement. So therefore, we just say that the product of 3 consecutive whole numbers is always divisible by 3. And that's all we need to do for this one. My little square just means the proof's complete. That's optional, I just like doing it. Question 2. Simplify root 2 times root 18. Well, root 2 times root 18 is the same as root of 2 times 18, which is the same as 36. And root 36 is 6. Here, same idea, root 3 times root 12 is the same as root of 3 times 12, which again is the same as root 36. And that gives us 6. So why include this in the warm-up? It seems maybe slightly strange, but A, it's so simple, and B, it's basically the same question repeated. Well, the idea here is if you think about root 2 and root 18, root 2 is irrational, as is root 18, but we're taking an irrational number and multiplying it by a different irrational number, and you see that the answer can actually be perfectly rational. And same for part B as well. So we're going to use this idea later on in this session. Warm-up question 3. Prove that the difference between the squares of any two consecutive odd numbers is a multiple of 8. So I'm going to start by introducing a representative for these numbers. I'm going to say, let little n be a whole number. Let little n be a natural number. 1, 2, 3, 4, 5, and so on. So if n is a whole number, then what we can say, thinking of the nth term of the odd numbers, an odd number is a multiple of 2 plus or minus 1. So we can say that 2n minus 1 is an odd number. The next odd number after 2n minus 1 will be 2 higher than this. So the next odd number after 2n minus 1 will be 2n plus 1. So if n is a whole number, then 2n minus 1 and 2n plus 1 are going to be consecutive odd numbers. The next thing we need to do in this question is show about the difference between them. We need to show that it's a multiple of 8. Well, to find the difference between anything, you take the bigger thing and subtract the smaller thing. So here, though, we're interested in the squares of these odd numbers, not the odd numbers themselves. So we take the bigger one, square it, and then minus off the square of the smaller odd number. So we're going to do 2n plus 1 all squared. I'm going to subtract away 2n minus 1 all squared. So first of all, 2n plus 1 all squared. 2n squared gives us 4n squared. Multiply 2n by 1 and double it. So 2n times 1 is 2n. Double that gives us 4n. And 1 squared is 1. In fact, I'll colour code this so you can just see where it's all coming from. So 2n plus 1 all squared we have here. We're now going to subtract away 2n minus 1 all squared. So we're not dealing with negatives everywhere. I'm just going to think of a 2n minus 1 all squared here, where we can deal with this minus after. So 2n squared is 4n squared. 2n multiplied by minus 1 is minus 2n. Double that product gives us minus 4n. And minus 1 multiplied by minus 1 gives us plus 1. So what we've done here is I've put 2n minus 1 all squared into these brackets. We can now think about what will happen when we do this, subtract that. Well, 4n squared minus 4n squared, the 4n squareds will just cancel, as will the positive ones. So plus 1 minus plus 1, the units will cancel as well. However, 4n minus 4n is the same as 4n plus 4n, which is 8n. And 8n is quite obviously a multiple of 8, because it's 8 multiplied by n, which was the whole number we started with. And so we've got to this stage, so we've pretty much proved it. So just conclude by referring back to the initial thing you're wanting to prove. So just as long as you just write this, it makes it easier, even though it is a bit of a pain. So just write something along the lines of, therefore, the difference between the squares of any two consecutive, hate all this writing, but there you go, consecutive, whoops, not whole, odd numbers, consecutive odd numbers is a multiple of 8. And then we're done. Lastly, question 4. So use the factor theorem to find a factor of the function f of x equals 2x cubed plus x squared minus 16x minus 15. So the factor theorem tells us if we can find a root of a function, then a factor of it will be x minus that particular root. So we're just going to hunt now for an actual root of what f of x could be. So let's just try f of 1. So we want to find an input which gives us an output of 0. If it's not 0, we don't really care. We only care if it's 0 or not. So if x is 1, 2 times 1 cubed is 2, 1 squared is 1, minus 16 times 1 is minus 16, minus 15. I don't really care to work this out, but all I can see here is it's clearly going to be negative, so it's clearly not going to be 0. So that is not going to be equal to 0. So let's try maybe 2. 2 times 2 cubed, well 2 cubed is 8, 2 times 8 is 16. Plus 2 squared, so plus 4. So far this is 20. But now we need to minus 16 times 2, so we're minusing 32, so it's gone negative again. And minus 15, it's even more negative, so that's not worked either. Next we can try 3. Again, what I'd suggest you actually do is to do this on a calculator. And in fact, so I'm not going to be a complete hypocrite, I'm going to show you how you do this on a calculator now actually. So just makes it easier, less chance of you making a slip. So f of 3 is 2 multiplied by 3 cubed plus, then plus x squared, so we're going to add 3 squared, minus 16x, so minus 16 times 3, then minus 15. And what do you know? We have 0, so we know that 3 is a root. So just writing that in, so 2 times 3 cubed plus 3 squared, minus 16 times 3, minus 48 minus 15. That does equal 0, as the calculator showed us. And so what this tells us now, using the factor theorem, is that x minus 3 is a factor of f of x. By the factor theorem. Now part B is saying to use your answer from part A to divide f of x by a suitable factor. We now have a suitable factor, we've got x minus 3, and then fully factorise f of x. So x minus 3, I would suggest, is our suitable factor. Then we can factorise f of x. So division can take a bit of space. So I'm just going to give myself a bit more space to do this one. So I'm going to do it over here. And then we can think about fully factorising it after we've done the division step. So just popping it over here. So we're going to take the polynomial, which is this, I'm going to divide it by this factor, which was x minus 3. So we're dividing 2x cubed plus x squared minus 16x minus 15 by x minus 3. So you might get quite rusty with polynomial division, so this is a great opportunity to just refresh yourself on how to do it. So first of all, we do 2x cubed divided by the highest power of x in the dividend. So 2x cubed divided by x, that's going to give us 2x squared. Next, we multiply this by the x minus 3. So 2x squared multiplied by x is 2x cubed. And 2x squared multiplied by minus 3 gives us minus 6x squared. Next, we subtract. We subtract 2x cubed from 2x cubed. This will always cancel. X squared minus 6x squared. That gives us 7x squared. And before we divide again, we need to always remember to bring down the next term in the divisor, which is minus 16x. Now we go again and divide. So we divide the highest power of x from this step, which is 7x squared, by the x here. So 7x squared divided by x gives us plus 7x. Next we multiply. So 7x multiplied by x minus 3, 7x multiplied by x is 7x squared. And 7x multiplied by minus 3 gives us minus 21x. Now again we subtract. The 7x squareds cancel. Minus 16x minus minus 21x is minus 16x plus 21x, which is 5x. Then we need to remember to bring down the next and the final term. So this next step will be our last one because we've brought down everything. So now we divide again. So 5x divided by x leaves us with positive 5. Now we multiply. 5 multiplied by x minus 3. 5 times x is 5x. And 5 multiplied by minus 3 is minus 15. And what do you know? When we do this subtraction now, we'll have 0, no remainder, which is what we'd expect, of course, because we knew from part A that x minus 3 is an exact factor of what we're dividing. So let's now have a look at what we've got. So the quotient, the answer if you like, is this thing here. So we can now say, therefore, 2x cubed plus x squared minus 16x minus 15 equals x minus 3, because x minus 3 was the initial factor, multiplied by this, which is 2x squared plus 7x plus 5. So it does say in bold, fully factorised, which is sort of like a nice little hint that maybe this will factorise again, and indeed it does. So x minus 3. Now we need to think of two numbers that multiply together to give us 10, using the AC method. 2 times 5 is 10, yet add up to 7. Those two numbers are 2 and 5. So we can rewrite the 7x squared as a plus 2x and a plus 5x. So now we have x minus 3. And in here, we can factorise out a 2 and an x and write x plus 1. And here has a common factor of 5, so we can write this as 5 lots of x plus 1. And so, writing the 2x plus 5 in its own bracket, we now have the final factorised form, which is x minus 3, brackets 2x plus 5, brackets x plus 1. And that's finally fully factorised. Now, at this stage of the year, I often give you a few little nods and hints about how you can use your ClassWiz to help you out in these situations. So before we move on to the lesson proper, I'm just going to show you how you could have factorised this using the ClassWiz. So get your ClassWiz ready, press the menu button, and scroll along until you get to option A, equation/func. Press equals to enter this mode. Now we're solving or wanting to solve the roots of this polynomial here, this expression involving x squared. So press option 2, and it's degree 2 because it's a quadratic. And so what we're going to do is solve for when this would be equal to 0, and based on the outputs, that will tell us how it factorizes. So our x squared coefficient is 2, our x coefficient is 7, and our constant term at the end is 5. So press equals, and it will solve it. So one root is minus 1, and so what that means is one factor is x plus 1. And so this minus 1 relates to the plus 1 here. So what you do is you take this number, swap the sign, if it's a minus make it a plus, and just bang an x in front of it. So the factor is x plus 1. The second root is slightly harder to interpret, so press equals for the second root. This relates to the second factor. Again, you swap the sign, so make that plus 5 over 2. But this 2, bring it up and to the left. That 2 is the coefficient of the x. So this is 2x plus 5, which relates to that one. So it can take a bit of getting used to in terms of how the calculator links to the roots and the factors, but it's well worth investing the time to get comfortable knowing how the ClassWiz helps you to factorise quadratics and also even cubics and quartics. So, worked example 1. Use a counterexample to prove that the following statement is false. N squared minus n minus 1 is a prime number for 6 to 10 inclusive, where n is a member of the natural numbers. So n has to be a counting number, so that excludes decimals or fractions. And so proof by counterexamples, like I mentioned earlier, they're not too hard at all, as long as you don't get yourself muddled and know what it means. All it means is we just need to find one particular case, no more, no less, just one case where the statement happens to be false. And so we can try 7, 6, 8, 9 or 10, and if just one of those gives us a number that isn't prime, that shows that the statement is generally speaking false. So let's start and do it systematically, starting at 6. So let's try it for when n equals 6. So when n is 6, we're going to have n squared, which is 6 squared, minus n, which is minus 6, minus 1, which gives us 29. So that is actually prime, so that holds true there. So keep going, no luck yet. Let's try when n is 7. When n is 7, we're going to have 7 squared minus 7 minus 1, and that would come out on a calculator as 41. 41 is still prime, so we've not proven it to be untrue yet. But if we were to try when n is 8, what we'd have is 8 squared minus 8 minus 1, which is 64 minus 8 minus 1, which equals 55. And 55 isn't prime because 55, for example, equals 5 times 11. So in other words, this is not prime. So because we found a counterexample, we've disproved this statement here. So therefore it's not true when n is 8, so the statement is false. So not true when n equals 8. So the statement is false. Let's have a look at the second worked example. So worked example 2. If m and n are irrational numbers where m isn't the same as n, then mn is also irrational. Disprove this statement by means of a counterexample. So this is where warm-up question 2 could be helpful. So we can use the same examples in warm-up question 2 even, or we could adapt them. So what I'm going to do here, I'm going to say we can let m be root 2 and n we could make root 8. So m and n are both irrational. Root 2 is irrational and root 8 is irrational as well. But then if we work out the product, nm, or mn rather, then mn is going to be root 2 multiplied by root 8. Root 2 times root 8 is the same as root 16, which is 4, which is rational, because 4 can be written as an exact fraction. 4 is 4 over 1. It certainly isn't a decimal with a non-recurring pattern. And so we've therefore shown that this statement here is false. And that's all there is to it. Just find one example where it doesn't hold true, and we've proven the statement to be generally speaking false, where in this case, the statement just happens to be this bit in the inverted commas, in the quotation marks. Example 3, again another proof by counterexample here. So let p, q and r be non-zero real numbers, and consider the statement: if pq is greater than r, then p is greater than r over q. So state with a reason whether the statement is always true, sometimes true, or never true. Before we proceed, it's worth just thinking about how one statement links to the other. This is called an implication. If one statement, then another. So could this be rearranged into that? Hopefully you can see that actually all we're doing to get from this one to that one is dividing through by q. So if you divide by q, we end up with this here. But also notice, very importantly, we're talking about an inequality in this case. So hopefully this should ring some alarm bells from GCSE work you should have done. We can divide through an inequality without having to change the sign of the inequality symbol if all values we're multiplying or dividing by are positive. And so if p and q are positive, then we can divide through by q and there'll be no problems at all. So the tip here is to be thinking about it's an inequality, so negative numbers might have something to do with this disproof. So what I'm going to suggest here is we just make up some numbers for p, q and r and just see what drops out. So I've said it's to do with positives and negatives perhaps. So let's try a scenario where, first of all, we have it that p is 3, q is 2 and r is 4. And so if that's the case, what we'd have is that pq would be 3 times 2, which is obviously 6, and we'd have that 6 is greater than r because r is 4. So that's true. And if we work out r over q, if r is 4, then that's 4 over q, which is 2. So p is greater than r over q, so we can say that holds true. since our value of p we have, which is 3, is greater than r over q, which we worked out was 2. So in this initial case, it's true. So we can just say the statement is true for when p is 3, q is 2, and r is 4. But what about if p or q or both were negatives? And so what I want to do now is just adapt this initial condition and say that, let's say for example, p were minus 3, q were minus 2, and r was 4. It's possible, by the way, that you've tried different values to me. I'm not saying you have to pick 3, 2, 4, and then minus 3, minus 2, and 4. But the important thing here is to try q being positive and then q being negative. And you'll get that it's true for one and not true for another. So let's say p is minus 3, q is minus 2, and r was 4. Then what would happen now is that pq will be minus 3 multiplied by minus 2. Minus multiplied by minus is a positive, which is 6. So in this case, pq is greater than r, is true, because our pq is 6 and it's greater than our r, which is 4. But r over q now, if we're letting our r be 4, then that becomes 4 over our q, which is minus 2, and 4 over minus 2 equals minus 2. So p being greater than r over q is not true now. Since our p, which we said was minus 3, is that bigger than r over q? If r over q is minus 2? Is minus 3 bigger than minus 2? No, it's not. That isn't the case. So therefore, in this case, the statement is false. So we just say the statement is false for these conditions. So false for when p is minus 3, q is minus 2, and r is 4. So I've just shown that it's true in some instances and false in other instances. Therefore, generally speaking, we can say that the statement is sometimes true. Sometimes it's true, like over here. Sometimes it's false, like on the right-hand side. The last working example I've got is this one here. So we've got this algebraic statement, x plus y over 2 is equal to or greater than xy. Show, by means of a counterexample, that this inequality is not true when x and y are both negative. So we're sort of almost given the answer here. Just pick any values of x and y which are both negative and show that it's not true. So what I'm going to do here is just pick nice, easy enough numbers. I'm going to go for x being minus 2 and y as being minus 8. Then let's just consider the left-hand side separate to the right-hand side. So the left-hand side of this is x plus y over 2, which should now equal minus 2 plus minus 8 over 2. Minus 2 plus minus 8 is minus 10. Divide that by 2, we'd get that's equal to minus 5. And so just by considering the left-hand side of this inequality, which is this bit here, we get the left-hand side as minus 5. Let's now compare and contrast this with the right hand side. Which is this root xy. So root xy would be the square root of minus 2 multiplied by minus 8. Minus 2 times minus 8 is 16, and the square root of 16 is 4. And so if we picked our x and y as minus 2 and minus 8, we get that root xy is 4. So comparing these two, we can now say, but minus 5, is that greater than 4? Obviously, no, it's not. So that proves that the statement is not true. So therefore, we just conclude by saying the statement is not true. When x and y are both negative. And that's all there is to it. So I'm hoping you found those 4 worked examples useful and a template for how to do some on your own, which is what I'm going to ask you to do now. So, in your books, page 153, exercise 7e, and I want you to have a look at questions 5 and question 6, and then question 9 and question 10, which will give you some more practice on these. And by the end of doing all these exercises in chapter 7, you should be fairly well versed on these algebraic methods. I hope you've enjoyed that chapter. I think that's quite a nice chapter to cover. If you have any questions, please do, as ever, email me or ask me in class, and keep working hard. First and foremost, keep plugging away. Thanks once again for listening and tuning in. I'll see you all again soon. Bye.